Okay, we're starting something very different in Algebra 2. We're jumping into arithmetic and geometric sequences, which really work quite a bit with different types of patterns. And really, this is a pattern recognition problem. We're given this problem, it's in page 1 on our packet, and we have a 5 by 5 white square grid. You can see right here we've got 1, 2, 3, 4, 5 squares going left to right. And likewise, if we were counting vertically, we'd have 1, 2, 3, 4, 5. So it's a 5 by 5 white grid. But in this problem, they're saying this is like a school cafeteria. Outside that 5 by 5 grid, they start to alternate colored tiles. Here we can see it looks purple. On your packets, they might actually look black, just by the way that they have been copied. But the question is, can we count up, or can we find the number of purple tiles or black tiles here without having to count them one by one by one? So there are many ways you can do this. What you're really trying to do is look for groups. Look for groups and patterns. And like I said, this is really our sequences day 1, just dealing with one particular method. We're going to make several other videos showing different methods as well. But what some kids are going to do is they're going to say, look, if we just look at, say, this bottom portion, just look at the bottom part of that white grid there, you can see that maybe some of you might look and see that you almost have a trapezoidal kind of a shape down there. We've got 1, 2, 3 squares here and 1, 2, 3, 4 down below. So you can see that we'd really have 7 total. You could also imagine that these squares here would just push down. You'd have 1, 2, 3, 4, 5, 6, 7. But hopefully you're going to notice that there appears to be symmetry, and there is. This is what we mean by, can we count these up quickly without counting them one by one by one? Do we see a pattern? And look at this. We could maybe draw a real quick rendition and say here's a 5 by 5 by 5 kind of a pattern, and it sure looks like this is 7. This right here would be 7. This right here would be 7. And then over here would be 7. Altogether, that's 7 times 4, and 7 times 4, or 4 times 7 if you'd rather. I think a lot of times kids might say there are 4 groups of 7. You could do it that way. You can see that there would be 28 colored tiles here. So that's fine. It's certainly not the only way you could look at grouping these tiles. Our ultimate goal, however, is to see if perhaps we could find this pattern to be true in other scenarios. Eventually, we want to deal with just an arbitrary number of tiles, an n by n. But look, what if we had a 3 by 3 kind of a white grid in the middle right here? You could say, can you do the same thing? Well, now if we had a 3 by 3, you can see that, well, we'd have 1, 2, 3, 4, 5 black squares or colored squares here. You know what? I'm going to write my 3's inside just so it's going to make things look a little bit nicer. But could we still group things the way we just did? Yeah. We could say, look, here'd be a 5, and here'd be a 5. This way, we'd say we'd have 5. This way, we'd have 5 also. So in other words, with a 3 by 3 grid, we've got 4 groups of 5. There'd be 20 tiles all together. So this is a really cool way to be able to count things up quickly. But look, we could deal with a much bigger grid. What if we had a 7 by 7? And, you could say, well, if we've got a 7 by 7 and you can real quickly count 1, 2, 3, 4, 5, 6, 7 right here, you might wonder how many black tiles we'd have in this little grouping. Well, you can count them up individually, but I think you might see, hey, if I just slide these down, I've got 7 here, and I've got 1 to the right, 1 to the left. Sure looks like we'd have 9, doesn't it? And likewise, if we were to group around here, if we were to group around here just as well, what are we really seeing? Well, we could say here's a 7 by 7 by 7 by 7. Here's 9. Here's 9. You get the idea. And it doesn't take you too long to say, well, all these black tiles, I've got 4 groups of 9. 4 times 9 is 36. So tell you what, if we just do a real quick recap, we started off with a 5 by 5, right? And we said, hey, you're going to have all these groups. You might say, how many were in each group? Well, if we went right back to the 5 by 5, you saw it was 7, right? So we had 7s here. Said, well, then we looked at a 3 by 3. You'd say, well, once again, you had something very similar. Obviously, not as many black tiles. Let's see, what did we find? Well, it was 5s. And then we just saw a moment ago with the 7 by 7 white tiles. You'd say, how many black ones did we have? Well, you can still see the top of the screen up there. Looks like we had 9. So I guess what we were saying in class, if you're watching this video, you likely were absent when we were going over it. What I said in class was, oh, you know what, our course team, Mr. Olson, Mr. Clifford, and I, you know what, we forgot to throw in another one of these grid problems, alternating tiles. Doggone it, we forgot the 8 by 8 by 8. The 8 by 8 white grid. And then you'd think, well, wait a minute, how many black tiles would be there? Now, here's the beauty of it. Hopefully you're seeing a pattern here. Hopefully you're seeing a pattern. When you're saying, hey, when we had a 5, there were 7 in each group of a 5 by 5 grid. When we had a 3, that went to a 5. When we had the 7 by 7 grid, we had 4 groups of 9. So the question is, what relationship are you seeing? If you start with this 5 here, 5 by 5, what did you do to get to 7? If you started with a 3, what would you do to get to a 5? If you start with a 7, what would you do to get to a 9? Is there a pattern? Well, think about your basic math skills. You could say, what can I do to a 5 to get up to a 7? You might think, well, I can add. Add how much? Add 2. You'd say, well, let's see, if I started at a 3, oh, look at that, I'm adding a 2. Oh, how about the 7 going to a 9? Look at that, I'd add a 2. Wow. So guess what? If this pattern were to continue, we would guess that we would have 4 groups of 10. We would guess that we'd have 40 tiles altogether. Well, you might have seen earlier that ultimately the big question is, can we come up with a pattern for n by n? You'd say, what does the n by n mean? It means it's a non-specified number of rows by columns here. You think, oh my goodness, I don't know how to do that. Well, wait a minute. if that's the case, that this pattern is still going to hold true, what did you do whenever you started somewhere, no matter where you were starting, if you're starting with a 5, a 3, a 7, or an 8, or an n, what did we do each and every time? We added a 2. So what would we expect? We'd have n plus 2 algebraically. We'd have 4 groups of n plus 2. Look at that. So what do we think? This would be 4 times n plus 2. And by the way, you could most definitely distribute and get 4n plus 8. So this would be the total squares that you would have. 4n plus 8. We've come up with a formula if I know that I have an n by n white grid to start with. Let's see if it works. Here's what I'm getting at. When it was 7 by 7, that would mean n would equal 7. I would plug that in. 4 times 7 plus 8. 4 times 7 is 28. 28 plus 8, I am so sorry, is 36. Look, it checks. Wow. 4n plus 8. Would it work for this problem right here? Well, it's a 3 by 3. That means let n equal 3. 4 times 3 plus 8. 4 times 3 is 12. 12 plus 8 is 20. Look at that. It checks. We've come up with a formula to help us. Look right here. We've got a 5 by 5 grid. You'd say, well, if this formula is true, the total square should be 4n plus 8. With a 5 by 5, we're going to let n equal 5. 4 times 5 plus 8. That's 20 plus 8. Guess what we get? 28. It matches. So that's the power of generalizing and being able to find this pattern. We found that for an n by n, the total number of black squares would be 4n plus 8. And that is just one method that some people could count up the squares. We could look at another one and see how that would relate and see if we'll get the same formula.